Okay, welcome back everybody. So today is a very important lecture. So we're talking about porosity. In the very first lectures when we were talking about groundwater resources and availability amounts, I already introduced porosity a couple times, talking about, when we were calculating how much groundwater there is in the ground, that Corzorn paper where we just assume, let's say 20% porosity, and then 200-meter deep, groundwater wells, and then how much is that? So we already used it, and conceptually we understand this is basically the amount of voids, but today we take a deeper look into porosity. Again, the basic definition of porosity, right, is the amount of void divided by the total volume times 100. So here, right, the amount of voids divided by the total volume times 100. So it's just the percent volume that is holes, right? In the matrix, there's like solids and there's holes. So this is just the percent of holes, that's porosity. So a very simple definition. Now, what is the actual porosity of natural formation? So here's a simple example, right? So if we consider cubic packing, so this is what a cubic packing looks like here on the left, right? Where basically the sediment are all spheres, right? And they're packed one on top of each other, right? So you can see here they touch only by the tippy top, okay? So if we have a packing like this, right, the holes, the voids in the middle, we can calculate fairly easily, right? Let me just remove some of these blue lines, okay? So here the porosity is going to be the cube of 2r, so 2r is just the diameter, right? Minus the volume of the sphere. So if you think of it, right, if we take a cube with that ball inside, right, so the cube is 2r, or diameter, on the side, right? So 2r cubed is the total volume minus the volume of the sphere, the 4/3 of pi r cubed, right? So if we remove the volume of the sphere to the total volume, right, and again we want this to be a percentage, so divide that by the total volume, that gives us the volume of the voids, the percent volume of void. So if we just make those calculations, right, run through the calculations, we realize that the porosity in this case, for this specific case of the cubic packing, is about half, so 0.5, 50%. So in general, the real porosity is less than this, right? So this is sort of the high estimate, almost the maximum porosity you could ever have is about 50%. Because, well, there's several reasons, right? The first one is, well, you don't have perfect spheres, and they're not, even if you had perfect spheres, they wouldn't stack up, one on top of each other like a cubic packing. They would probably stack as a rhombohedral packing. We'll see that in the next slide. So they would, occupy some of those pores. Also in real life, right, there's like different grain sizes. So obviously smaller grains are going to occupy some of those voids and fill them up. So really you never have that 50% porosity almost. So here's the example for the rhombohedral packing. So you would see that a more stable, right, distribution, instead of having them stack on top of each other, is just like kind of the more stable, one half packing, right, where they actually touch in 2 points here. So if you calculate, if you do the same little exercise we did before, right, but for this configuration, you see that the porosity is already 26%, and that's a much more realistic number. So this is already a high-end porosity, but that's pretty common to see like 25-30% porosity. Actually, when you use like, when you just want to do back of the envelope calculation, 25-30% is a good rough estimate of porosity in general. One important note here is that I never gave you a size for the grain, right? So porosity doesn't really depend on the size of the grain. You could have like huge boulders or, silt, right? As long as they're little spheres, the porosity you can calculate without numbers, without diameters. So it's basically a scale-free parameter. It doesn't depend really on the size of the grain. So here's the other example where you can see, that filling by smaller and smaller particles, right? So if you have different particle sizes, right, then they're going to fill in, and of course your porosity is going to be much smaller. This is adapted from that Seaton et al. Recent paper. I really like the graphics of this, and also what's interesting is that you have density distribution at the top here. So right here, right? So what this is telling us is that there's a lot of those larger particles in this soil, right? Whereas on the right-hand side, if you look at it, right, you can see that the matrix, there's not that many of those large ones, and there's a ton of those little ones, so you can see the distribution here is much more uniform, okay? So we'll talk about this in 1 second. One way we can find the distribution of grains in a soil, a traditional way, is just to sieve it, right? So you pass a sample through a series of sieves, right, standard sieves, and this is, US sieve standards, and you can see that the sands here, sands and gravels are the coarser material, of course, and then you get to the coarse sand, the fine sand, and then the fines are everything that falls below the 200 sieve. So anything that's below like 0.07 millimeters is going to be considered like fines. And you can see here, sizes. So boulders are like big things like basketballs, and then cobbles, coarse gravels, right? And then the sands, and then the fine sand, and then below the sands is all the silty stuff, right? So again, important to remember sort of the classification. You don't have to remember specifically, each category, obviously, but have a sense of what a boulder cobble is versus like a coarse sand or a gravel, right? So those big categories. Now here are some grain size distribution. So once you've sieved through all the sieves, right, you can calculate, what is the percentage of, the coarser stuff and then the finer stuff, and then you can plot all that on a graph. And here are two different examples, and you can see already that this curve here is much more broadly distributed than this curve here that has a much sharper drop, right? I don't know if you can hear the rain, but it's raining over here. Okay, so this sharper drop here tells that this distribution is much narrower, right? So it's all the material is basically within one class, whereas here, right, it's distributed across classes. Basically, there's a much broader grain size distribution. And one way to identify or to quantify, how broadly distributed that grain size distribution is that uniformity coefficient, right? And what you do is you take the D60 over the D10. So D60 is the size class where 60% of the sediment is finer, and D10 is the class size where 10% of the sediment is finer, right? So when you take the ratio of that, you have a ratio. So if the ratio is high, right, that means that it's broadly distributed. Those, there's a lot of D60 is large compared to D10. If you have a small number, like here, the coefficient of uniformity, that means D60 is not that far from D10, so things are narrowly distributed. Oftentimes, again, I said before, you can take like 20 to 30% as your sort of standard back of the envelope porosity when you don't know. What we use typically for other calculations, and we'll go into more aquifer properties in the following lectures, but the D10 is typically your effective grain size, sorry, not porosity, grain size here. So you take the D10 and that gives you sort of what the grain size is in that material. Sometimes we use D50, but oftentimes D10. Okay, and that concludes our brief overview of porosity with a little bit more detail. And then in the next lectures, we'll move on to other aquifer properties. Thank you.